In 1967, an American KH-8 reconnaissance satellite passed silently over the Caspian Sea, photographing Soviet naval facilities as it had done hundreds of times before. The film was recovered, developed, and delivered to CIA analysts at Langley, Virginia. What they saw made no sense. There, floating on the water near the Caspian coastline, was something impossible. An aircraft, but not just any aircraft. This thing was enormous, longer than a Boeing 747, with stubby wings that seemed far too small to lift such a massive fuselage. And painted clearly on its tail were two letters, KM. The analysts brought in aviation experts. They brought in naval engineers. They brought in physicists. Nobody could explain what they were looking at. It was too big to be a conventional aircraft. The wings were wrong. The engines were positioned strangely, clustered at the front. And it was sitting on water like a boat. One analyst finally said what everyone was thinking. The Soviets have built some kind of monster. The name stuck. The Caspian Sea Monster. And for years, that's all the West knew about it. But this wasn't a monster. This was the realization of one man's obsession, a vehicle that existed in the gap between sea and sky, flying on a cushion of compressed air just 20 feet above the waves. The Soviets called it an Ekranoplan, a ground effect vehicle, and it represented one of the most radical aircraft designs ever attempted. To understand why the Soviets built it, you need to understand their problem. During the Cold War, the United States Navy dominated the world's oceans. American aircraft carriers could project power anywhere on the planet. The Soviet Navy, trapped in landlocked seas and frozen ports, couldn't compete directly. Soviet admirals were desperate for a solution. They needed something that could move faster than ships, but cost less than aircraft. Something that could evade radar and submarine detection. Something that could deliver troops or missiles to distant coastlines before the enemy even knew it was coming. Traditional military thinking offered no answers. Ships were too slow. Aircraft were too expensive and vulnerable to air defense. Submarines couldn't carry enough cargo. So the Soviets did what they always did when conventional solutions failed. They turned to their engineers and said, "Build us something impossible." And one engineer, a brilliant and obsessive designer named Rostislav Alexeyev, said yes. He'd been dreaming of such a machine for years. He called it a winged ship. The Americans would call it a monster. This is the story of the most bizarre aircraft ever to fly. A vehicle that broke every rule of aviation and somehow worked. A machine that could have changed naval warfare forever. If only it hadn't been so utterly impossible to control. Rostislav Yevgenyevich Alexeyev was born in 1916 in Novozybkov, a small town in western Russia. From childhood, he was obsessed with speed. Not just speed on land or in the air, but speed on water. He believed that boats were fundamentally inefficient, that dragging a hull through water was a primitive solution to transportation. By his 20s, Alexeyev had become fixated on a concept called hydrofoil technology. Instead of pushing a boat through water, why not lift it above the surface on underwater wings? Reduce drag, increase speed, revolutionize water transport. In 1951, Alexeyev became chief designer at the Central Hydrofoil Design Bureau in Gorky, now known as Nizhny Novgorod. He was 35 years old and already considered a maverick genius. The Soviet government gave him resources and freedom, rare commodities in Stalin's USSR. Alexeyev delivered results. His Rakita hydrofoil boat entered service in 1957, carrying passengers along Soviet rivers at speeds previously impossible for water transport. His Meteor hydrofoil followed in 1959, even faster and more elegant. These weren't just boats. They were demonstrations that Alexeyev's radical thinking worked. But Alexeyev wasn't satisfied. Hydrofoils were limited by the fact that their wings operated underwater, where drag was still significant. He wanted something faster, something that could fly. Then he discovered ground effect. Ground effect is an aerodynamic phenomenon that occurs when an aircraft flies very close to a surface. The air compressed between the wing and the ground creates a cushion of high pressure that dramatically increases lift and decreases drag. Pilots know ground effect as that floating sensation just before touchdown. For a few seconds, the aircraft seems to glide effortlessly. Alexeyev had a radical thought. What if you could sustain that effect? What if you built an aircraft specifically designed to fly permanently in ground effect, just a few meters above the water? The advantages were staggering. You'd get 70% more lift efficiency than conventional flight. You could carry enormous weight with relatively small wings. You'd fly too low for radar to detect effectively. You'd move faster than any ship, using less fuel than any aircraft. But the challenges were equally staggering. Flying that close to the surface meant zero margin for error. A slight pitch change could send you crashing into waves. Weather conditions would be critical. Pilots would need extraordinary skill. Alexeyev didn't care about the challenges. He saw only the possibilities. In 1960, he presented his concept to Soviet military officials. A massive ground effect vehicle capable of transporting troops and equipment across water at aircraft speeds. Invisible to radar. Able to land on any beach. Faster than destroyers, cheaper than transport planes. The military was skeptical but intrigued. The Soviet Navy desperately needed asymmetric solutions against American naval superiority. This qualified as asymmetric. They gave Alexeyev permission to build a prototype. Not a small test model. A full-scale operational vehicle. The Soviets didn't believe in thinking small. Alexeyev assembled his team at the design bureau. They would be working on the most classified project in Soviet aviation. The security designation was top secret, special importance, the highest level possible. Workers were told nothing about what they were building until they arrived at the facility. The project received an innocuous designation, KM. Officially, it stood for Korabl Maket, meaning prototype ship. But everyone at the design bureau knew it really meant Korabl Maket, ship prototype, the first of its kind. Alexeyev told his engineers they were building a vehicle that would fly faster than any boat and carry more than any aircraft. A vehicle that would exist in the boundary between sea and sky. They thought he was insane, but they'd seen his hydrofoils work, so they got to work building his monster. The KM was built in secrecy at the Krasnoye Sormovo factory in Gorky between 1964 and 1966. The specifications were absurd by any measure of aviation engineering. Length, 92 meters, longer than a Boeing 747. Wingspan, 40 meters, which seemed impossibly small for an aircraft that size. Maximum takeoff weight, 544 tons, heavier than most commercial airliners fully loaded. And it would fly just 5 to 10 meters above the water surface, at speeds approaching 500 miles per hour. The design was unlike anything that had come before. The fuselage was enormous and boat-shaped, with a high cockpit positioned at the front. The wings were short and stubby, mounted high on the fuselage, and clustered on the forward fuselage were 8 massive Dobrynin VD-7 turbojet engines, the same engines used in the Myasishchev M for strategic bomber. 2 more engines were mounted on the tail, bringing the total to 10 engines producing a combined thrust of over 100,000 pounds. All 10 engines would be needed just to get the KM airborne. Once in ground effect, 8 would shut down to conserve fuel, leaving only the 2 tail engines running for cruise flight. The construction challenges were immense. The KM had to be strong enough to withstand the structural loads of high-speed flight, but light enough to achieve lift with those small wings. Alexeyev's team used aluminum alloys throughout, riveting together thousands of panels into a structure that looked more like a ship than an aircraft. But the biggest challenge wasn't construction. It was testing. How do you test an aircraft that can't take off from a runway? The KM was designed to operate exclusively over water. Its flat boat-like hull made runway operations impossible, and no test facility in the Soviet Union could accommodate something so large. The solution was audacious. Once assembled, the KM would be transported to the Caspian Sea and tested directly in operational conditions. No wind tunnel testing of the full airframe. No gradual expansion of the flight envelope. They would assemble this massive vehicle, take it to the water, fire up the engines, and see if it worked. If it didn't work, 544 tons of aircraft would crash into the Caspian at high speed. Everyone on board would die instantly. The KM was transported to the Caspian in sections by barge in late 1966. Reassembly took months. Soviet engineers worked under canvas covers to hide the vehicle from American spy satellites. Security was absolute. Armed guards patrolled the facility perimeter. Workers lived in isolated compounds. Families were told they were building experimental hydrofoils. In December 1966, the KM was ready for its first test. The test pilot was a veteran named Vladislav Kotenko, one of the few pilots in the Soviet Union trusted with such a dangerous mission. He'd flown everything from fighters to heavy bombers. But he'd never flown anything like this. Kotenko climbed into the cockpit with his flight engineer and several observers. The cockpit was bizarre, combining aircraft instruments with maritime navigation equipment. Throttle controls for 10 engines dominated the center console. The view forward was excellent, like a ship's bridge, but the windows were aircraft-style and pressurized. They started the engines one by one. All 10 VD-7 turbojets roared to life, producing a sound described by witnesses as apocalyptic. The entire Caspian coastline could hear it. The water around the KM churned white from the exhaust blast. Kotenko advanced the throttles. The KM began moving across the water, accelerating slowly at first. At 50 knots, the nose lifted slightly. At 80 knots, the entire vehicle rose out of the water, riding on a cushion of compressed air between the hull and the surface. At 120 knots, the KM lifted completely into ground effect flight. It was flying 10 meters above the Caspian Sea. 544 tons of metal and fuel, suspended on nothing but compressed air and raw engine power. Kotenko later described the sensation as surreal. The vehicle felt stable, almost too stable, locked into ground effect by aerodynamic forces. The ride was smooth, far smoother than any aircraft he'd flown. The engines produced tremendous noise, but the cockpit was surprisingly quiet. He flew the KM for 20 minutes on that first test, never climbing above 15 meters, never exceeding 200 kilometers per hour. When he landed, touching back down on the water and throttling down the engines, the entire test crew was waiting on the shore. Alexeyev was crying. His impossible dream had worked. Over the next year, test flights continued. Pilots gradually expanded the performance envelope. Speed increased to 300 kilometers per hour, then 400, eventually reaching 500 kilometers per hour in level flight. That's over 300 miles per hour, faster than most World War II fighter aircraft, for a vehicle that weighed more than 4 modern fighter jets combined. The KM could cruise for hours using just its 2 tail engines, covering distances over 1,500 kilometers. It could turn, though slowly and carefully. It could operate in moderate sea states, though rough water was dangerous. It worked. Against all rational expectation, Alexeyev's ground effect vehicle worked. The Soviet military now possessed a vehicle unlike anything in the world. A vehicle the Americans didn't know existed, didn't understand, and couldn't counter. At least, they didn't know yet. That was about to change. The spy satellite had been in orbit for 3 months when it passed over the Caspian Sea on June 21, 1967. Its high-resolution camera system was designed to photograph Soviet military installations, missile sites, naval bases. On this particular orbit, it was imaging the Caspian coast near Kaspiask. The satellite captured its images on film, which was physically ejected from orbit in a re-entry capsule. Air Force cargo planes caught the capsule mid-air as it parachuted to Earth, a procedure so dangerous and complex that it succeeded only 70% of the time. This time it worked. The film made it to the National Photographic Interpretation Center in Washington, D.C., where analysts developed it and began the laborious process of examining thousands of images. Then someone noticed something strange in frame number 847. At first, they thought it was a ship, but ships don't have wings. Then they thought it was a large aircraft that had crashed and was floating in the water. But the image showed no damage, no debris field. The vehicle appeared intact and operational. Senior analysts were called in. Aviation experts examined the photographs with magnifying glasses. The vehicle was huge, at least as long as a strategic bomber. The wings were wrong, too small and positioned too high. The engines were clustered strangely at the front of the fuselage. And painted on the tail, clear as day, were 2 large Cyrillic letters. Nobody knew what it meant. Nobody knew what they were looking at. The image was classified top secret umbra and distributed to only a handful of officials with appropriate clearances. CIA analysts gave it a code name, the Caspian Sea Monster. The Pentagon demanded answers. Was this a new type of bomber? A seaplane transport? Some kind of hybrid aircraft carrier? Intelligence agencies scrambled to gather more information. Additional satellite passes were scheduled. Signals intelligence stations monitored for radio traffic related to the mysterious vehicle, but information was scarce. The Soviets had kept the KM program extraordinarily secret. No signals intelligence indicated its existence. No human sources had reported it. The satellite photograph was the first and only evidence that something unprecedented was happening on the Caspian Sea. Defense analysts began producing estimates. If the Soviets had built one, they were probably building more. If this vehicle could carry troops or missiles at high speed, it represented a significant threat to NATO naval forces. American aircraft carriers could be vulnerable to fast-moving threats that flew too low for radar detection. Strategic planners began developing countermeasures for a threat they didn't understand, against a vehicle they'd only seen once, in a single satellite photograph. The Caspian Sea Monster had entered Western military consciousness, but it would be years before anyone understood what it really was. To understand what made the KM extraordinary, you need to understand how it flew, or more accurately, how it skimmed. The KM never truly flew in the conventional sense. It existed in a unique regime of flight called ground effect, operating in the thin boundary layer between sea and sky. The physics that kept it airborne were radically different from normal aircraft. Here's how it worked. When the KM moved forward at high speed, its stubby wings pushed air downward. That air compressed between the wings and the water surface, creating a cushion of high-pressure air. This cushion generated tremendous lift, far more efficiently than wings operating in free air. The effect was powerful but temperamental. It only worked when flying very close to the surface, between 5 and 10 meters above the water. Fly too high, and the high-pressure cushion disappeared. The KM would lose lift and drop back toward the surface. Fly too low, and the wing tips could clip the waves. Pilots described it as surfing on an invisible wave of compressed air. The slightest pitch change had enormous consequences. Pull back on the controls, and the nose would rise, but instead of climbing like a normal aircraft, the KM would simply slow down as it left ground effect. Push forward, and the vehicle would accelerate but drop dangerously close to the water. The takeoff sequence was particularly intense. All 10 engines would be brought to full power while the KM was stationary on the water. The combined thrust of over 100,000 pounds would overcome the enormous water drag and accelerate the vehicle forward. At 50 knots, the hull would begin rising out of the water, transitioning from displacement mode to planing mode. At 80 knots, the vehicle would rise onto its step, riding on just the aft portion of the hull. At 120 knots, the KM would lift into ground effect, and the hull would clear the water completely. Once airborne, the pilot would carefully climb to the optimal cruise altitude of 8 to 10 meters. Then, one by one, 8 of the 10 engines would be shut down. Only the 2 tail-mounted engines remained running, providing just enough thrust to maintain speed in ground effect. This cruise configuration was remarkably efficient. The KM could maintain 400 to 500 kilometers per hour using just 2 engines. Fuel consumption was far lower than conventional aircraft of similar size. Range extended to 1,500 kilometers, sometimes 2,000 kilometers in optimal conditions. But the ride was strange. Unlike conventional aircraft that could maneuver freely in 3 dimensions, the KM was locked to the surface. Turns had to be gentle and gradual. Bank the wings too steeply, and one wing tip would dip toward the water while the other rose out of ground effect, causing unpredictable behavior. Weather was critical. The KM could operate in sea states up to 3 meters, but anything rougher became dangerous. High waves meant the ground effect cushion became inconsistent. The vehicle would bob and pitch as it flew over wave crests and troughs. In really rough seas, flight was impossible. The cockpit was unlike any other aircraft. The instrument panel combined aviation equipment with maritime navigation tools. Altimeters were useless at such low heights, so pilots relied on radar altimeters that measured distance to the water surface with extreme precision. The view from the cockpit was spectacular. Flying 8 meters above the water at 500 kilometers per hour gave pilots a perspective no one else experienced. The horizon stretched endlessly in all directions. The water rushed past below in a blur. Sea spray occasionally hit the windscreen during high-speed runs. Pilots reported that the KM felt stable and solid in cruise flight, almost like a boat. But that stability was deceptive. One wrong control input could send the vehicle into an unrecoverable situation. Several test pilots described near misses where the KM nearly struck the water during routine maneuvers. The crew consisted of 10 people: pilot, co-pilot, flight engineer, navigator, and 6 technicians who monitored the engines and systems. Everyone wore flotation vests. Ejection seats weren't installed because ejecting at 10 meters altitude was pointless. If something went wrong, you had maybe 2 seconds to react before impact. And yet, despite all these dangers, the KM performed admirably throughout its test program. It proved that ground effect flight was viable, that enormous vehicles could travel at extraordinary speeds using a fraction of the fuel conventional aircraft required. The Soviet military was impressed. They wanted more. They wanted armed versions that could hunt American carriers. They wanted the Caspian Sea Monster to evolve into something even more fearsome. But first, they needed to keep it from killing its pilots. Between 1966 and 1980, the KM conducted hundreds of test flights over the Caspian Sea. Soviet engineers meticulously documented its performance, pushing the boundaries of what ground effect vehicles could achieve. Test pilots gained experience with the unique handling characteristics. Improvements were made to the control systems, engines, and structural components. But ground effect flight remained unforgiving. The margin between success and catastrophe was measured in meters and seconds. Several near disasters occurred during the test program. In 1968, a pilot misjudged his altitude during a high-speed turn. The left wing tip struck a wave crest, sending the KM into a violent roll. The pilot managed to recover, but the wing sustained significant damage. The vehicle had to be towed back to base for repairs that took 3 months. In 1972, engine failure during takeoff nearly ended in catastrophe. One of the forward engines ingested debris and exploded, sending shrapnel through the engine nacelle. The pilot aborted takeoff, but the KM was already traveling at 80 knots in ground effect. Bringing it back down onto the water at that speed was like controlled crashing. The hull took massive structural damage, requiring extensive repairs. In 1975, a test flight in deteriorating weather conditions almost proved fatal. Sea state increased during the flight, and returning to base meant flying through 3-meter swells. The KM pitched and rolled violently as it traversed the rough water in ground effect. One particularly large wave struck the hull, cracking several structural members. The pilot barely made it back. Each incident taught lessons. Each near miss resulted in modifications. But the fundamental challenge remained. The KM was operating at the absolute edge of controllability. Pilots needed extraordinary skill, constant vigilance, and frankly, luck. The Soviet Navy evaluated the KM's operational potential. Could it actually be used in combat? Could crews be trained to fly it reliably? Could it survive in contested maritime environments? The answers were mixed. The KM could certainly move troops and equipment faster than any ship. It could potentially evade radar detection by flying below the radar horizon. But it was vulnerable to small arms fire, couldn't operate in bad weather, and required highly skilled crews. Still, the test program continued. The KM logged thousands of hours of flight time. It became a familiar sight over the Caspian, this enormous vehicle skimming impossibly close to the water at improbable speeds. Rostislav Alexeyev, now in his 60s, continued overseeing the program. He pushed for improved designs, better engines, military variants. His obsession with ground effect vehicles never diminished. He believed he was pioneering a new category of transportation that would revolutionize naval and air mobility. Then came 1980. On a routine training flight in December, the KM was conducting high-speed maneuvers with a relatively inexperienced crew. The pilot was being evaluated for certification to fly the vehicle independently. He'd completed dozens of supervised flights, but this was his first without a senior instructor pilot in the cockpit. The flight proceeded normally for the first hour. Standard speed runs, gentle turns, engine shutdown, and restart procedures. Everything by the book. Then, during a routine turn at 8 meters altitude and 400 kilometers per hour, the pilot made a critical error. He increased the bank angle too aggressively, while simultaneously pulling back on the controls, attempting to tighten the turn radius. The KM's right wing rose out of ground effect while the left wing dipped toward the water. The vehicle lost lift asymmetrically and rolled further. The pilot attempted to correct, but over-controlled in the opposite direction. The KM snapped into a violent roll oscillation. Within 3 seconds, the left wing struck the water at 400 kilometers per hour. The impact forces exceeded the structural limits of the airframe. The wings separated from the fuselage. The vehicle cartwheeled across the surface, disintegrating as it tumbled. 6 crew members died instantly in the initial impact. 4 others were thrown clear and survived, suffering severe injuries. The pilot and co-pilot died when the cockpit section sank in over 200 meters of water. Salvage attempts were made, but the KM had broken into dozens of pieces scattered across the sea floor. Recovery was deemed impossible. The wreckage was left where it fell. The Caspian Sea Monster was dead. The prototype that had flown hundreds of successful missions, that had proved Alexeyev's theories correct, that had terrified Western intelligence analysts, now lay in pieces at the bottom of the Caspian Sea. The era of the giant Ekranoplans appeared to be over. But the Soviet military wasn't ready to abandon the concept. They wanted something smaller, more controllable. They wanted a weapon. The loss of the KM didn't kill the Ekranoplan program. Instead, it forced Soviet designers to rethink their approach. The KM had been a test platform, a proof of concept that was too large and too complex for practical military use. What the Soviet Navy needed was something more refined, more lethal. Enter Project 903, the Lun-class Ekranoplan. Design work had already begun in the mid-1970s, based on lessons learned from the KM program. The new vehicle would be smaller, more maneuverable, and purpose-built for a specific mission, anti-ship warfare. Its target would be American aircraft carrier battle groups. The Lun, which means Harrier in Russian, represented a completely different philosophy from the KM. Where the KM was a massive experimental prototype, the Lun was a sleek predator. Where the KM carried test equipment and observers, the Lun would carry missiles. The specifications were impressive. Length, 73 meters, significantly shorter than the KM. Wingspan, 44 meters. Maximum takeoff weight, 380 tons, lighter and more agile. Top speed, 550 kilometers per hour in ground effect. Range, 2,000 kilometers. But the most significant feature was its armament. Mounted on the forward fuselage were 6 massive P-270 Moskit anti-ship missiles, known to NATO as SS-N-22 Sunburn. Each missile weighed 4 tons and could travel at Mach 2.5, making them among the fastest anti-ship weapons in the world. The tactical concept was revolutionary. The Lun would launch from a Soviet naval base, fly at high speed just meters above the water, approach an American carrier battle group below radar detection range, then pop up briefly to acquire targets and launch all 6 missiles simultaneously. By the time American radar detected the Lun, 6 Mach 2.5 missiles would already be inbound. American carriers had defenses against conventional threats. Fighter aircraft could intercept bombers hundreds of miles away. Surface-to-air missiles could engage cruise missiles. But a ground effect vehicle that appeared suddenly at close range, launched supersonic missiles, then disappeared at 500 kilometers per hour? That was a nightmare scenario for carrier battle group commanders. Construction of the first Lun began in 1983 at the Volga shipyard in Nizhny Novgorod, the same facility where the KM had been built. Security was even tighter this time. The entire assembly hall was covered with camouflage netting to prevent satellite observation. The design incorporated improvements learned from the KM's test program. Better flight control systems, more reliable engines, enhanced structural strength in critical areas. The cockpit was modernized with better instrumentation and visibility. 8 Kuznetsov in K-87 turbofan engines provided power, mounted in a similar configuration to the KM. 6 on the forward fuselage for takeoff boost, 2 on the tail for cruise. But these engines were more efficient and more powerful than the KM's power plants. The first test flight occurred in July 1987. Test pilot Anatoly Melnichenko lifted the Lun off the Caspian Sea and put it through its paces. The vehicle handled better than the KM, more responsive and stable. The smaller size and improved aerodynamics made a significant difference. Over the next 4 years, the Lun underwent extensive testing. Weapons systems were validated. Mission profiles were practiced. Crews were trained. The vehicle proved capable of sustained high-speed flight and ground effect, could operate in sea states up to 3 meters, and could launch its missiles with accuracy. NATO intelligence became aware of the Lun-class existence in 1988 when satellites photographed it during outdoor testing. The images triggered alarm in Western naval circles. Intelligence assessments concluded that the Lun-class represented a genuine threat to surface vessels, particularly in restricted waters like the Mediterranean where detection and response times would be limited. American carrier battle groups modified their defensive postures to account for potential Ekranoplan attacks. Radar operators were trained to watch for low-altitude, high-speed contacts. Electronic warfare systems were updated. New tactics were developed. The Lun entered limited operational service with the Soviet Navy's Caspian Flotilla in 1989. It was designated as a missile strike Ekranoplan. Western media dubbed it the Duck of Death, a nickname that Soviet crews found simultaneously insulting and amusing. Plans called for building 8 Lun-class vehicles to patrol Soviet maritime borders. Factory space was allocated. Materials were stockpiled. Crew training programs expanded. But by 1989, the Soviet Union was collapsing. The economy was in free fall. The Communist Party's grip on power was weakening. The Cold War was ending, not with nuclear fire, but with bankruptcy and disillusionment. And suddenly, nobody cared about building flying monsters to hunt American carriers. The Soviet Union's economic crisis had been building for years, but by 1989 it reached catastrophic proportions. Defense spending consumed nearly 20% of GDP, a burden no economy could sustain. Factories struggled to meet production quotas. Supply chains collapsed. Workers went unpaid for months. Military programs were evaluated ruthlessly for cost-effectiveness. The Ekranoplan program didn't fare well in this assessment. Each Lun-class vehicle cost approximately 100 million rubles to build, equivalent to multiple conventional warships. Operating costs were astronomical due to the massive fuel consumption and specialized maintenance requirements. And for all that expense, the Ekranoplan could only perform one mission: anti-ship strikes in relatively calm waters. The Soviet Navy's budget was slashed repeatedly through 1989 and 1990. Plans to build 8 Lun-class vehicles were canceled. Then plans for 4 were canceled. Eventually, only the single prototype remained operational, and even that was flying increasingly rare missions as fuel and spare parts became scarce. Rostislav Alexeyev, the visionary designer who'd started it all, died in 1980, shortly after the KM's crash. He never saw the Lun become operational. He never knew that his life's work would be abandoned within a decade. His successor at the Central Hydrofoil Design Bureau tried to keep the program alive. They proposed civilian variants for passenger transport. They suggested cargo versions for remote regions. They argued that Ekranoplan technology represented valuable intellectual property that shouldn't be abandoned. Nobody was listening. The Soviet government had more pressing concerns, like preventing total economic collapse and maintaining basic services. In 1991, the Soviet Union dissolved. The Lun became the property of the Russian Federation, which had even less money than the USSR had possessed. The single operational vehicle was effectively mothballed, sitting at a naval base in Kaspiask on the Caspian coast, rarely flying, slowly deteriorating. Other Ekranoplans suffered similar fates. The Lun-class transport Ekranoplans, smaller vehicles designed to carry troops and light vehicles, were retired and abandoned. These vehicles had actually seen limited operational service during the Soviet-Afghan War, transporting Special Forces troops. But by the mid-1990s, they were rusting in storage facilities. The Central Hydrofoil Design Bureau struggled to survive. Without military contracts, the Bureau had no income. Engineers were laid off. Design documents were archived. Test facilities were closed. Some former Bureau engineers emigrated, taking their knowledge to other countries. A few joined commercial aerospace companies. Most simply retired, their expertise in ground effect vehicles utterly useless in the new economic reality. The Lun sat in Kaspiask for nearly 30 years, slowly decaying. Local authorities considered it a curiosity, occasionally showing it to visitors, but unable to afford proper preservation. The missile launchers were removed for safety. The engines were cannibalized for parts. Paint peeled from the titanium skin. Satellite images from the 2000s and 2010s show the Lun deteriorating year by year. What had been a sleek predator became a rusting hulk. Weeds grew around the landing gear. The cockpit windows cracked. Seabirds nested in the engine intakes. In 2020, the Russian government finally decided to move the Lun to a museum. Not because they valued its historical significance, but because it was becoming an eyesore at the naval base. The vehicle was loaded onto a barge and transported to Derbent, where it was supposed to become the centerpiece of a Patriot Park military museum. The journey didn't go well. A storm damaged the Lun during transport. When it arrived at Derbent, the vehicle was in even worse condition than when it left Caspian. Museum officials scrambled to secure funding for restoration, but money was scarce. The Lun sat in its new location, still deteriorating, waiting for restoration that might never come. The KM, the original Caspian Sea Monster, remained at the bottom of the Caspian Sea. Occasionally, divers reported seeing sections of wreckage during underwater surveys, but no serious salvage attempts were ever made. The titanium structure would take centuries to corrode in the saltwater environment. The Lun-class vehicles were scrapped or left to rot at various military storage facilities. A few ended up as museum pieces, but most were simply abandoned. By the early 2000s, Russia's Ekranoplan program was effectively extinct. The technology existed only in archived design documents and fading memories of elderly engineers. The massive investment of resources, the decades of research, the brilliant innovations, all apparently wasted. The Ekranoplan concept didn't die. It went dormant, waiting for technology and economics to catch up with Alexeyev's vision. From a purely engineering perspective, the KM and Lun programs had failed for understandable reasons. Ground effect vehicles occupied an awkward middle ground between ships and aircraft. They required specialized facilities, highly trained crews, and perfect weather conditions. They couldn't operate in rough seas. They couldn't fly over land. They were too expensive for cargo transport and too limited for military operations. But the technology they pioneered was sound. The aerodynamic principles were valid. The efficiency gains were real. The problem wasn't the concept itself, but the execution in a Cold War context where cost was secondary to capability demonstrations. In the 21st century, interest in ground effect vehicles began returning, driven by different motivations than Soviet military ambition. China became the most aggressive pursuer of modern Ekranoplan technology. The Chinese military saw potential applications for island resupply, amphibious operations, and rapid transport across the South China Sea. Chinese aerospace companies began developing small-scale ground effect vehicles in the 2000s. By 2014, reports emerged of Chinese test flights of vehicles called Tianyi, or Flying Wing. These were smaller than the Soviet designs, typically 10 to 20 meters long, intended for cargo and passenger transport rather than military strikes. Chinese engineers studied declassified Soviet research and incorporated modern materials and control systems. The Chinese military's interest was strategic. The South China Sea contains hundreds of small islands and reefs that China claims. Supplying these outposts requires either slow ships or expensive aircraft. Ground effect vehicles offered a middle option, faster than ships, cheaper than aircraft, and difficult for adversaries to intercept. Russia itself began reconsidering Ekranoplans in the 2010s. The Central Hydrofoil Design Bureau, still in existence, proposed a new design called the A-050 Chaika, or Seagull. This vehicle would be much smaller than the Lun, designed for civilian cargo transport and search and rescue operations. The A-050 specifications were modest, 9 meters long, carrying 3 passengers plus cargo, cruising at 200 kilometers per hour. It represented a practical approach to ground effect technology, prioritizing reliability and economics over pure performance. Prototype testing began in 2016. Videos of the Chaika skimming across Russian rivers and lakes appeared online, generating significant interest. The design incorporated modern composite materials, computer-controlled flight systems, and efficient turboprop engines. It looked nothing like the massive Soviet monsters, resembling instead a sleek sports car with wings. But perhaps the most significant revival came from an unexpected source, the United States military. In 2023, DARPA, the Defense Advanced Research Projects Agency announced the Liberty Lifter program. The goal was to develop a large seaplane capable of operating in ground effect, transporting heavy cargo across oceans, and landing in austere environments without port facilities. The Liberty Lifter concept looked remarkably similar to Alexeyev's original vision, just with 21st-century technology. The proposed vehicle would have a wingspan of 100 meters, carry 100 tons of cargo, and cruise at ground effect altitudes using modern turbofan engines. DARPA's interest stemmed from logistics challenges in the Pacific. In a potential conflict with China, U.S. forces would need to supply island bases across thousands of miles of ocean. Traditional cargo aircraft require runways. Ships are slow and vulnerable to submarines and missiles. A ground effect vehicle could potentially bridge this gap. The program awarded contracts to aerospace companies to develop detailed designs. Wind tunnel testing began. Computer simulations validated the aerodynamics. By 2024, the Liberty Lifter had progressed from concept to serious development program. Engineers working on Liberty Lifter openly acknowledged their debt to Soviet Ekranoplan research. Declassified KM and Lun technical documents were studied extensively. The lessons learned from decades of Soviet testing informed modern design decisions. Other countries began exploring the technology. South Korea investigated ground effect vehicles for inter-island cargo transport. Singapore examined their potential for search and rescue operations. Even private companies started developing small recreational ground effect craft for wealthy enthusiasts. What changed? Why was the concept viable now when it failed in the Soviet Union? Several factors made the difference. Modern materials, particularly carbon fiber composites, were lighter and stronger than the aluminum used in Soviet designs. Computer flight control systems could manage the tricky ground effect regime far better than human pilots. GPS navigation eliminated the dangerous low-altitude navigation challenges. And modern turbofan engines were more efficient and reliable than Soviet-era turbojets. Most importantly, the mission requirements changed. The Soviets built Ekranoplans to hunt aircraft carriers and demonstrate technological superiority. Modern developers focused on practical applications: cargo transport, humanitarian relief, search and rescue, island logistics. The economic equation shifted too. Modern manufacturing techniques reduced costs. Commercial applications could potentially generate revenue rather than just consuming military budgets. The technology became not a weapon system, but a transportation solution. Academic research expanded dramatically. Universities in Russia, China, the United States, and Europe established research programs studying ground effect aerodynamics. Papers published in aerospace journals explored new wing designs, control algorithms, and operational concepts. What had been secret Soviet military research became open international collaboration. Startup companies began appearing, proposing civilian ground effect vehicles for everything from luxury passenger transport to cargo delivery in remote regions. Most were vaporware and unrealistic business plans, but some showed genuine promise. The dream Alexeyev pursued in secrecy under Soviet military control was being rediscovered by a global community of engineers, each adding modern innovations to the fundamental concept he'd proven viable. The Caspian Sea Monster's true legacy wasn't military dominance. It was demonstrating that ground effect flight could work at large scale, that the aerodynamic principles were sound, and that the efficiency gains were worth pursuing. 60 years after the KM's first flight, Alexeyev's vision was finally being realized, not as a weapon, but as a solution to 21st-century transportation challenges.